Greetings and welcome to NautelNav's webinar. Welcome, worldwide audience. My name is John White. I'm the head of marketing and product strategy at Nautel. I'll be your host today. Our topic today is NAVDAT technology. It'll be a review and a modulation demo. So today we'll do a quick introduction. We'll do a look for some of our audience just to get everybody caught up. We'll do a review of NAVDAT. We'll take a deeper dive into the digital and the specifics of NAVDAT modulation. We'll introduce new products, our NAVDAT transmitters and NAVDAT modulator. And then we'll look at the actual modulation and have some time for questions. Assisting today is Herman Zensen. He's a sales manager for Nautel for Europe, and Herman brings a very capable background for the discussion today. Herman is an engineer and has had a long history involved in digital transmission, DAB, DRM, and so all that background is very relevant to the digital modulation techniques that are used for NAVDAT. Also assisting today is Gary Gilbreth. He's our sales manager for navigation for Nautel. And Gary has a long history with Nautel. Originally did RF design. And Gary will probably fade in the background during the presentation, but he'll be available for questions later on in the presentation. So let's get underway. Just a bit of housekeeping. You'll notice the GoToWebinar system that we're using today has the ability with a little orange button to create questions. And so we'll keep an eye for your questions. We may hold most of them for the end of the presentation, but if there is an opportunity for us to answer them as we move through, we'll review them as we go. So first of all, for many of you may know that Kenta Technologies and Nautel joined together roughly about 2 years ago. And what's very important when it comes to NAVDAT is that we have three kind of focus areas that really position us well for the future of navigation and NAVDAT broadcasting. Together, we're the world's largest NAVTech supplier. And I spoke about the specifics of Herman's background, but both our companies share a very extensive history in digital transmission and the complexities of modern day complex digital signals. And then also, Nautel especially has had a history of building high power transmitters, over 20,000 of them installed around the world, as high as 2 megawatts of power. And that becomes very relevant as we move from NAVTechs into NAVDAT type signals. So very quickly, for those who maybe just have a very cursory understanding of NAVDAT, let's take a look at where it fits in. So NAVTechs historically has been a very basic teletype type communications protocol, very robust. But given today's use of graphics and better safety at sea type information, navigation information, really it's the move to allow much more complex communications. And so NAVDAT, really meaning navigational data, is designed to transmit this much more richer type of data to ship systems. It's really developed as a successor to NAVTechs and uses digital radio broadcasting. And you can just begin to imagine the broad range of communications that will be capable with a graphical higher bandwidth capability. So in summary, it has an enhanced range and reliability, a higher data capacity, we'll talk about that quite a bit, multimedia capability, even potentially video, and flexibility as well. So moving forward, I'm going to hand this over to Herman, and he'll take us through a bit of NAVTechs versus NAVDAT and into the modulation aspects. Herman?
Yes, hello everybody. Good morning, America. Good afternoon, Africa and Europe. And good evening, Asia. And good night, Australia. It seems we have people from everywhere in the world on this webinar. Thank you very much for joining us. And yes, so just some slides we have shown already in the last webinar, but just to remind you what's the relationship between NAVTEX and NAVDAT, because we think most of you will come from a NAVTEX background. Just show the next slide. Yeah, thank you. Yeah, so basically, yeah, what NAVTEX is a subset of NAVDAT. Okay, you can look at it from an application point of view. So you know, NAVTEX is there for transmitting text messages. Okay, so the application would be a text application, and obviously NAVDAT can also transmit text messages. Yeah, but also from a technology point of view, they are compatible because if you can do a NAVDAT modulator, it's also quite easy to do a NAVTEX modulator. Okay, so we will come to this in detail. Here you can see, yeah, this is the big differences in the modulation. Okay, you can see the NAVTEX modulation is a analog modulation, 300 Hertz bandwidth. The NAVDAT would be, in any case, a higher bandwidth, so it's rectangular spectrum, more complex spectrum. We'll come to this, and it can be any bandwidth between 1 and 10. It can be 1, 3, 5, and 10 kilohertz bandwidth. Okay. So just to explain, yes, the NAVTEX signal is a simple signal, easy to imagine. Okay, you just switch between two frequencies. Okay, so you know the NAVDAT frequencies is 490 and 518 kilohertz in the MF band. Okay, and yeah, you can have. It's easy for us to imagine, you know, and we see the signal here, the time signal of the NAVTEX signal. And it's also on one carrier only. It's only one carrier that is always on the same power. Okay, so it means that the TX power, the peak, we call it peak envelope power, is always it's just one power, the same power. Yeah. Whereas in the NAVDAT, we come to a much more complex signal. In the time domain, it would look like like a noisy signal, like noise. Okay, very, very, you know, with high peaks, high peak noisy signal. And this gives some challenges also to the transmitters and the whole transmission chain. We will talk about it again. Okay. Then you can show the next slide. Yeah, this slide we have shown again. We repeat it because it's really very important that you see that NAVDAT, yeah, we can transmit more data, but we also need more bandwidth in the RF spectrum. So historically, the standard was designed, you know, initially only for 10 kilohertz, and then we added the other bandwidth. So we have now lower bandwidth, but compared to NAVTEX, we would have only 300 Hertz. So it's a big difference, and it has significant implications for the transmission chain. It means not only the transmitter, but also the ATU and the antenna. Okay, we mentioned this in the last webinar. And here we come now to the heart of the webinar. This is really now about explaining the digital modulation in the first step, and then we will also show you some snips of the standard we have. And this part should help you to understand better the standard. Okay. Yeah, digital modulation, what it is, it's always, we call it co-FDM technology. So if the whole world would be coded, orthogonal, frequency division multiplexes, not easy for non-native speaker to pronounce all this. So it's a big word for what? Yeah, you can see the last word, part of it is frequency division multiplex. So it means already we have segments and frequency. And we also have fragments in time. Okay, so this leads us to cells. So we always, in digital modulation, you have always to think, you know, it's not enough just to think in time. You always have to think in time and in frequency domain. And I added this on the right side, okay, for the engineers, you know, okay. So to come from the frequency to time, you would have an inverse Fourier transformation. From time to frequency would be a Fourier transformation, yeah. And these are not only, you know, this is not only mathematics in our products. For example, for a modulator, you would typically have an IFFT, which is an inverse fast Fourier transformation, which is a quite complex algorithm, which takes a little bit of calculating power. And this is also why these digital modulation is not so old. Yeah, we have products for this. Let's say the first products were in radio broadcasts and television broadcasts at the beginning of the 2000s. So this is due to the components that didn't have enough transmission power. So now the easiest way, you can show next, yeah, thank you. The easiest way, so we transmit information within a cell, okay? Segment and segment in time and frequency. So the easiest way to do this would be to say, okay, we just take a sine signal, okay? So we will have when we talk about frequency, the frequency segment, this would be a subcarrier. Okay, so we don't have only one carrier as with NAVTEX. We have many carriers. Okay, that are in different frequency segments. Okay, so the sine signal is defined by a frequency. Then we have still two other things, amplitude and phase, on which we can play to transmit the digital information. Okay, and this brings us to the next slide, which is a little bit a different, how to say it, presentation of a sine signal. You can also present a sine signal as a complex vector. Okay, so here we call this an IQ diagram. Okay, so we have the real component and the imaginary component of and this the sine signal would then be a pointer. Okay, that has a length, which would be a vector that has a length, which is a, which is the amplitude, and a phase, which would be the phase. These are the two informations we mentioned before, and this pointer would turn around, at the speed of the. We'll not show you this. You would get dizzy with this. It would at the speed of the carrier frequency. Okay. You can show the next one. Yeah. Once we have said this, just come back to the one slide back. Yeah. Thank you. So. If you have, so how can we do now? We could, for example, we said we have phase and amplitude, okay? So we bring this in a modulation, we call this a quadrature amplitude modulation, okay? So quadrature amplitude modulation, what is it? So it's always quadrature because it's always a little bit like a square. And here you can see we have 4 different states, okay? The amplitude is always the same, but we have 4 different phases, each, 90 degrees separated, okay? This type of modulation we will call a 4QAM modulation, okay? And with a 4QAM modulation, you can transmit 2 bits, basically, okay? So then let's look at the next one. The next one is this slide is to explain you why these IQ diagrams are very popular and in people that work with this digital modulation, because basically it allows you to give an easy view, immediate view on the quality of the transmission channel. Okay, so for example, here you can see it's not only one point. You have many points around an ideal point. Okay, and the more points, the far away the points are, the more disturbed is the signal. Okay, and we have a measurement for this, which is called modulation error rate, which would be the ratio of the ideal vector, okay, that we saw before in the other diagram, and compared to the to the error vector, which would be from the ideal point to the real point. Okay, so this is a kind of it's in dB, typically expressed in dB. It's a little bit similar to the signal to noise ratio, and it's a typical measurement for all digital modulation. We have this. Okay, you can come to the next slide. Yeah, so we talked about 4QAM, but obviously we can have others. Okay. We can have 16 QAM, 64. So you see, it's always organized points. This is like American streets and towns. It's not like European streets. They're all well organized, in squares. And you can see that if we have 16 QAM, so we have 16 states. So 16 is 2.2 times 2 times 2 times 2. You can have 4 bits per carrier symbol. Okay. And 64 QAM, you can have 6 bits. So this means you have a way high, you can transmit more bits on 64 than on 4, okay? So now you would say, oh, this is good, then let's always transmit in 64. The only problem with this is why I've shown you the other slide before. Imagine you have a signal as we saw it before. Just come back to the first slide. Imagine you have a signal as before. You could imagine that it's quite difficult if you have points all around to exactly code and exactly say this point should be at this place and this point should be at the other place. So this is why this modulation is not very robust for disturbed channels. Okay, and what we need at the receiver side, we will need a higher signal to noise ratio to decode it, to be able to decode it. So this slide is from Phil Schmidt, so he gave some indications. So you can see that for 4QAM, we have 14 dB signal to noise ratio, and for 64, we would need 22, which is quite a big difference, okay? So here we have a first trade-off. You cannot have it all. So either you say we transmit more bits, but we need higher signal to noise ratio at the transmitter, which means higher transmitter power. Huh? Or we always say, okay, we have it more robust, but then less bits. Okay, then you can switch to the next one. Yes, this is another slide from Phil Schmidt. He has shown last time already, but I'll give you some more explanations on this now. So we can see, yeah, that this is a good explanation how we come to the time signal in digital modulation. So you can see on the very left, this is one carrier modulation, so as NAVTEX would be. So you can see transmitter power always constant. You know, if you start to add carriers, 3 carriers, it starts to move. Okay. 23, it moves even more, and 29, it's really moving. You know, it's similar to noise actually. Okay, so it's quite a, how to say it, it's astonishing, because we have this. You know, we have in the frequency domain, we would have a rectangular, quite mathematical spectrum, and here we have a noise similar to noise signal, which high peaks. Okay, so which brings us to something we would you need to could calculate the average power of the transmitter and compare to the peak powers, and we have something like 10 dBs difference. This is a lot, yeah, and this is yeah, unusual. This is not what we find in NAVTEX. Yeah? There's a big difference between both modulations, and you need to prepare your transmitter for this, but not only the transmitter for these peaks, but also the ATU and yeah, in particular the ATU and the antenna. Okay. Yes.
So Herman, I guess I was just going to interject. There's that saying that there's no free lunch, and so really, to achieve the promise of NAVDAT, it really requires these more complex modes and the broader bandwidth and the higher power that goes with it.
Exactly. So this brings us to a certain number of trade-offs that we have to take into account when you conceive the system. Okay. So just so we mentioned already the peak and the peak average power ratio in the last slide before. Okay, so yeah, sorry, just come back. Yeah, it's typically 10 dB. Okay, now the trick is, yeah, you could reduce it a little bit. If you reduce it, then you have higher coverage. Okay, because you have higher average power. But we come again to a trade-off. Okay, if you know, it can be configured in the modulator, the PIPR. So we have some small room on this. Okay, which can give you better coverage. But if you do this, then also the modulation error rate would be reduced. So it means, yeah, you have a higher disturbed signal. Okay, so you need the high peaks. You need the high peaks to, in the information theory, you need it. You need the height to have the information. Okay, it's like this. So same thing, we have another trade-off here. Okay, so you need to have in mind PIPR and MER. These are very important, how do you say it, measurements we have in digital modulation. And this is also why we recommend to do trials, because then you can, yeah, you can play a little bit and see how the whole what is the best setup in your case. Okay. So now we will, now this all I've said to you before, it was just about digital modulation in general. And here we come to now to digital modulation with NAVDAT. Okay, we will talk in this webinar, we'll talk about MF NAVDAT. Okay, so NAVDAT, the NAVDAT frequency is 500, but there are some others around 500, but typically it's 500 kilohertz. Okay, so in the, I will show you a first snip of the standard. Okay, so this is so here in this standard here you see, yeah, what is defined here. This is one of the very first tables in the standard. So you can see here what's defined. So you can see there are 2 modes. First thing, 2 modes. We have A and B. Okay, which is corresponds to day and night mainly, because you know in medium wave, so you know, in the propagation in night is higher, but you have also more echoes and reflections. So you need a this is why we define 2 modes. Okay, first thing, 2 modes. Second thing, you have lots of times here. You can see we have a useful time and then a guard interval, the total time, and yeah, what is this? The useful time, yeah, well, the useful time is the time, how to say, there's a relationship between the useful time and the carrier spacing. And this is where the O comes from. The orthogonality of the signal means, you know, is exactly this. There's a relationship between the symbol, the useful symbol duration, and the carrier spacing. Okay, so which is the inverse. The carrier spacing is the inverse of the. In our case, it would be for around 40 hertz in the case of NAVDAT. Okay, and we have around 20 milliseconds of useful time for the duration of the symbol. But now we added something, which is also very interesting, which is we add a little bit time, which is the guard interval. So what is this good for? Well, yeah, this is something. I mean, you come from analog, you hear this is very astonishing. But in the digital modulation, if you add a little bit of time, to your symbol the duration, it means all the echoes that come in, will strengthen your signal. Okay, the echoes that come after, they will. So you have same thing as with analog, but if you have a guard interval that is high enough, big enough, large enough to allow all the reflections to come in, you will have better reception in contrast to analog modulation. And this is also why you can have single frequency networks. In digital modulation, you can have two transmitters transmitting on the. If you respect the guard interval, they can transmit on the same frequency, and you have increased signal quality. Okay. So on the next one. On the next one, you can see, this is for the transmission frame. So we have a transmission frame of 400 milliseconds in NAVDAT. This is very similar to DRM. And then within this frame, we transmit 15 OFDM symbols, okay? And the whole thing starts with a synchronization symbol, okay? You need to have, so 400 milliseconds is in today, it's quite a time already, okay? It's not very short. So we have big frames, okay? And come back to the next one. Yes, so we defined carrier spacing, we defined the useful time, we defined the guard interval. Now, to have a complete view, we have the bandwidths. We mentioned already 1, 3, 5, and 10 kilohertz, and the number of carriers. And with this, we have defined our OFDM diagram, okay, our OFDM signal, okay. In theory, you can say with this, we know what it looks like, okay. So again, for A and B modes, we have different number of carriers, okay, you can see this. So this is the next thing that was defined and is defined in the standard, okay. So we have the carriers, the bandwidth, and the higher the bandwidth, the more carriers we can put in. And then, this is to explain you that if you come to the modulator, the transmission, we have three inputs. 3 inputs. So we have the data stream. Obviously, this is what we want to transmit, okay? And the data stream can be transmitted in 4, 16, or 64 QM, okay? Then, but we also have two other streams, and these streams are information streams are concerning signaling information. Why do we need these streams? Because you need to tell the receiver which bandwidth we have, which modulation is used for what, okay? So this is why we have the modulation information stream. This is always in 4 QM. This is because this is very important information for the receiver. If the receiver doesn't have it, it cannot work, okay? So we have it always in 4 QM, and it will transmit. What will it transmit? It will say which bandwidth we are on, and how do we modulate the TIS and the data stream, okay? And for the TIS, for the transmission information stream, we have then the information on the mode. We have some information on the transmitter and on the time. And this can be in 4 or in 16 QM. So it can be a little bit less robust, because if this doesn't, let's say there are errors in this time, it's less dramatic than for the miss. Okay. So these 3 channels, you can show the next one. So we have different cases now from what we told. So let's say we have the most robust case, okay? So we have 4 QM that we use for MIS, for TIS, and DS. Then you would only have the red points, the 4 red points in the signal. But if you have the most complex mode, with the highest data rate, so you would have then a MIS with 4 QM, you would have a TIS with 16 QM, and a data stream with 64 QM. Here you come to this diagram, which you see the receiver has to cope with all this. So it's getting it's getting lots and lots of constellation points. Okay, but this is what we see at the same time. By the way, the modulator. We talked about the modulator. So as I mentioned already, we have the 3 inputs. For the 3 information streams. Each stream, there will be treatment for these are bits coming in. Okay, and the bits. The first thing we will do, we'll scramble them. This is done with a polynomial shift register for the engineer. So it's just to make sure that you don't have regular patterns, okay? That you not have too many 000s and too many 111s, because this would not be good for the signal form, okay? So you have to scramble the whole thing with the energy disposal, and then you do a channel encoding. We come back to this later, but the channel encoding basically means you will add bits to do error correction, okay? And once you have done all this, so you have all the bits, then you need to say which bits would it be, transmitted on which subcarrier at which time segment. Okay, so you put, this is why we call it the OFDM mapper. This is to put in all the cells that we presented in our very first picture, the exact bits. Okay, after this, we would have an IFFT, which was also mentioned already, okay, to come, because we are still in the frequency domain, so we have still subcarriers with information, so we need to bring this to a time signal, and the time signal, in contrast to NAVTEX, would be a complex signal, okay, so we'll have two components. We would have an imaginary component and also a real component. We call this an IQ signal, okay. IQ signal here means it's a baseband signal, which presents a spectrum, okay. It's only presents a spectrum, and it's a sampled signal, okay, baseband signal. And this then you can transform in an RF signal by, you bring it to the right frequency, to 500 kilohertz in this case. And yes, you will also do some other calculations to bring it to the RF form, okay. One of the beauty of the systems we have with Nautel is that Nautel has already, the transmitters have already IQ inputs, okay. And if an IQ input is ready for one digital modulation, which is the case in Nautel because they're already ready for DRM, then you can also transmit automatically NAVDAT because it's exactly the same error, the pre-corrections and things like this, okay. Just information on this. And there was in the very low, you see the pilots. This is about the pilots. So what is the pilots? What the pilots are about? So the receiver, the pilots will help the receivers to get an idea about the transmission channel, to make it easy. So some of the symbols, some of the symbols we have, they are not transmitted. They're transmitted with a higher gain, 2, and they are transmitted in an even more robust modulation, which is the BPSK or 2QM, okay, which would be just 2 points in the IQ diagram, okay. And these are there. The transmitter will receive the signal, okay. The receiver will know what should be the signal on these pilots, okay. And with this, it can calculate, the channel qualities, and then also better decode all the carriers that are close to the pilots. This is how it works, okay. So so we have, you can see all the here in this diagram. So you have on the how to say it, in the vertical it's the time with all the time with the symbols one by one is 15 always, and then on the horizontal you can see these are all the carriers. The black points are the pilots, and then you have in front of each, the sequence of each symbol will start with the synchronization symbol, okay. Can go to the next one. So we talked about already, we saw this as a channel encoding. So we know transmission channels are not perfect, so they're also noisy. So we had already the guard interval, which was there to protect against echoes and reflections. Here we are more on something like, there could be, in the signal, a short-term burst or a noise or something like this, okay? So for this, we can add bits. The basic idea is we add some bits to correct errors, okay? We call this forward error corrections, okay? So by doing this, what would happen is, okay, you say, okay, we get a more robust signal, again, more robust, so you will have less errors, okay? But you will have less useful data rate. It's another trade-off here, okay? We call this a code rate. The code rate would be the ratio between the useful data rate compared to the total data rate, okay? There are different types of channel encoding, okay? While typically in broadcast we have convolutional, but here in NAVDAT, in the case of NAVDAT, we have what we call LDPC coding, which is one of the very last things we have. It's used in 5G, by the way. It's called low density parity code, which is supposed to be the last, the most modern and one of the best channel encoding we have today available. We have two code rates only in the standard, which makes it easier. It's 0.5 and 0.75. Okay, and then the next one. Yes, this slide we shown you last time already. This time, it's always the same thing. This is to illustrate to you, okay, the big difference you can have in the bit rates. But now you can get, you can understand a little bit better the columns, okay? So you see, for example, we have here, you have the bandwidth for each. This is for mode A, only mode A. This means the day mode. Okay, then we have the bandwidth. We have 10, 5, 3, 1, okay, kilohertz. Then we have the number of subcarriers linked to it. And we have the modulation type, okay. And with all this, what we have said before, then you can calculate how many bits we can transmit, okay. And we have the channel coding. The channel coding, you see there are two figures in the channel coding. the last figure, let's say the last figure is the total number of bits, and the outgoing bits, and the first figure is the incoming bits. Okay, so you can see, but for example, the first time we have 2,560. This is 2,560 bits coming in and 5,120 out. So it brings us to a code rate of 0.5. Okay, so we can have everything between 340 bits per second up to 28, almost 29 kilobits per second. Okay, so this is another example. Yeah, so it really depends on what mode you're using. Okay.
Well, Herman, I guess we're seeing the depth of complexity, and it certainly clarifies for me why our engineers have been so busy as they develop the modulator that we'll see in a moment.
Yes. This slide is another slide from last time. We have shown it already. It's a little bit linked to what I've said just before. Okay, because it's a tricky thing for example, for a Coast Guard. So typically we say here, okay, we gave you the typical example, 220 nautical miles. Okay, we took 10 kilohertz bandwidth. Okay, and here you can see in function of the modulation of if it's 4, 16, or 64, how many data rate we can transmit. And yeah, because what we mentioned, all the things we mentioned before, yes, you need to adapt. If you say we want to reach 220 nautical miles and we want to have this data rate at this modulation, this is the power we need. Okay, so you can calculate the transmitter power with this. So we can see, you would need 50 kilowatt. It starts to be a good transmitter. 50 kilowatt peak power if you want to transmit, for example, up to 29 kilobits per second. Okay, a typical case, let's say 10 kilowatt transmitter for 15 kilobits per second. Okay, so just to remind you again of this. And so we will just talk a little bit about our products. Okay, so the Nautel MF HF MF NAVDAT is like, we have two components. One is the modulator and one is the transmitter. Okay, so you will have the modulator in front of the transmitter, and then we have so the modulator is made here in France by the Kenta team. Okay, it is, we have some, as John mentioned before, we have some experience on DRM already. Okay, you can see, this it will obviously, it supports all the QAM modes I have presented to you, and also all the channels, means MIS, TIS, and DS. We have all the bandwidths. We have LDPC. There's one thing I would like to mention right away is that the standard, we have the standard is completely defined for the 10 kilohertz, but for the 1, 3, and 5, we would need to add some matrices for the LDPC. So we made some assumptions for this in our modulator to develop our modulator. Okay, so we have mode A and B for MF. And yes, the input, because we said, you saw in the diagram, we have the DS, TIS, and MIS. We use a DCP for this, which means distribution communication protocol. This protocol, well, there are others, but we use this because this is already used in the world of digital radio. This is used for EDI in the DAB, MDI in DRM, and also E2X for HD radio. So so we kept it like this. It's not defined the standard, so we did this, because it makes sense for sure to do it like this. So this is how we defined it. Okay, then we have the modulator. Obviously, has HTTP interfaces that you can, with a web browser, access to it. We have SNMP for the alarms. It meets the standard, and I will show you in the next slide a little bit different block diagram. So here you can see, so we get the IP in, which is DCP based, as I told you just. So we need to decapsulate IP and then get out TIS, MIS, and DS. Okay, we will then do all the things we saw before, the energy dispersal, we will do the channel coding, we will do the OFDM cell mapper and everything. And after this, we will synchronize perfectly at the same time. We will get out the IQ signal. And then we have a little bit more things to do around the IQ signal. We need to do a little bit more synchronization. We can add some buffer and delay if needed. And we transform this then to RF. So our modulator will have two outputs. One is IQ, which can go directly to the Nautel transmitter. And the other one is then RF. And we will show you after a short video with the output, the RF output of our modulators. Okay, so I hand over now to John, who will talk more about the Nautel transmitters then.
Sure. So Just a couple of weeks ago, Nautel and Kenta attended the SMMM show in Hamburg, Germany, and we introduced the first model of what will be the NAV series. It's the 25 kilowatt peak power version. It's a modular system with very good efficiency, and it's based upon a designs already proven within the Nautel family. The basis of the transmitter is the amplifier module, and it is, you could say, over-designed. It has the capability to do 12 kilowatts of continuous power. A very robust design, and in the NAV 25 transmitter, as example, there are two of these. Another aspect of the NAV 25 series is it uses a very advanced signal modulator. This is actually to create the RF signal. And so, you know, a traditional modulation would have, you know, far less granularity in its ability to create the signal. And by using a 6-phase modulator, and it's actually running at 1.8 mega samples per second, we're able to follow the modulation of the digital signal that's passed to the transmitter in exacting detail to avoid distortion. So the RF amplifier module, it's very modern design, so hot pluggable, no adjustments, very large overbuilt heat sinks. We know that these products have to go in and live in their environments, and very rugged environments for years, decades. Also considering that environment, there is extensive lightning protection, fast shutdown in case of bad VSWR and antenna situations. And then also these systems have a lot of attention to cooling. We use ball bearing fans, of course. The typical fan life is 9 years. And the overall transmitter is very efficient, so it doesn't produce much heat to begin with. So in summary, this is a very proven, efficient design. It's modular. It's designed from the ground up for a digital signal like the NAVDAT signal. We've installed over the last decade 35 megawatts of the cumulative amount of these systems worldwide, and once again the digital aspects of it. So from there, I believe we're going to take a look at how this starts to come into reality from a signal point of view and the modulation point of view. So I'm going to hand it back to Herman.
Yeah.
And we'll take a look at the simulations.
Yeah, thank you very much. Yeah, we'll show you two things. We have some simulations. These are simulations we have done, you know, our engineer has done, okay? You can see, yeah, this is a, you know, a constellation diagram, the IQ diagrams that I've shown you before, the ideal ones, okay? So here we have the case, NAVDAT case, MIS, TIS, and DS, and all on 4QM. So you can see, yeah, you have 4 points, you know, each point would be for, you know, for the 4QM, okay? And then you have also 3 points on the x-axis, you know? So what is this? These 3 points, so the middle, the 0, it would be the DC component, which is another thing, you know, you have a DC offset in the signal that you wouldn't have with NAVTEX, you know, it's another thing here, okay? DC, and then we have on the right and the left, this would be the BPSK modulation of the synchronization signal and also of the pilot signal, okay? You see on the right side, you see what I've shown you before, you know, the synchronization signal and the pilot signal, which explains to you why you have more than 4 points in this simulation diagram, okay? So basically what we did, we took, you know, our engineers, they put in the bits in a simulated modulator, and they, how to say, they did this a certain amount of time. So we found these, in this case, we have 7 points, yeah? Okay, then go ahead to the next one. So we come to where, so now we have a case, you know, MIS 4QM, TIS 4QM, and DS 16QM. So we add all 16 points for the 16QM. So you can see it's getting already more complex, okay? And in the next one, you can see, yeah, here we have, yeah, we have 4 for 4QM for MIS and TIS, and 64 for DS. And you can see there's some, because we did this only a limited number of time in the simulation, okay? some OFDM symbols are, no, how do you say, some of the constellation points are not used during this time. This is why you see the blank points in it. And if you come to the very last one, which was the most complex one, yeah. So this is the one, you know, with the red, blue, and green points. This is the same here, okay. So you can see, yeah, it's getting more and more complex, okay. Now, yeah, we will present you now a video, okay, with the output of our modulator. Just before starting, can you show the next slide without starting the video, John, or is it possible? Yeah. The next slide, you can see that if you look at the video, okay, so you should look first in the upper part, you will see the spectrum, okay. In the middle part, you will see the waterfall diagram over the time, and you should have a look at the bottom right, in the very bottom right corner. There you will see the different bit rates, okay. So then this just for you, this is you know, an interface of our modulator, okay. If you have the modulator, we have HTTP, you will have a measurement like this, okay. So we just, you know, our engineers they snipped it not to show too much, so not to, you know, the whole interface, just the interesting one for the RF characteristics. Okay, so let's start then.
So this is the real world. It's beyond theory that we looked at quite a bit, and it's beyond the simulations that we've looked at. This is an actual modulator creating a NAVDAT signal. So away we go. So you're seeing the time sequence.
This time will start. So for time being, we have this modulator is not yet switched on. Okay, then the 10 kilohertz, we have spanned 20 kilohertz. Okay, the 10 kilohertz signal starts to show up. Okay, and then yeah, the beauty of this thing is now yeah, we will switch over to other modes, to, you know, to 5 kilohertz. Okay, so you can see, yes, 10 kilohertz is there. We had 500 kilohertz here. Okay, total. Then we go to the 5 kilowatt, and then you see, look at the look at the bottom. I cannot see it here. Maybe you cannot see it. I'm not sure. I cannot see it here. It should be, you know, you should see that the bit rate is also changing, you know. Okay. This is again, I think we are still at 10 kilohertz here. Can you see the bit rate, John? I'm not the right thing. Should be something like 70 or 20 kilobits per second, you know. Then we show up, this is 5 kilohertz. Okay. We should be something like 10 kilohertz per second. Yeah, and I think we should come now to 3. Here we are at 3 kilohertz, and here it's the last one, the very last one, which would be a 1 kilohertz signal. Okay.
So all that complexity that we've been looking at is just hit the real world with a modulator.
Yes. Okay, and over to you, John.
Sure. So just a couple of slides to sum up everything we've looked at. We've definitely seen the complexity that's required to do NAVDAT modulation, but then that's the complexity that allows us to take a leap forward in what we can communicate. So all the coding is there, the bandwidths have been covered. And so, Nautel as a company now can build a complete solution based on both the modulator and the transmitter. So what's next? So next time we get together, we would look to show you a full transmission chain demonstration, feeding the system through the transmitter. As Herman mentioned, there's good definition for the 10 kilowatts mode, but the 5, 3, and 1 kilohertz modes are still waiting for the standards, the final standards definition of the LDPC channel coding. So that's our engineers will work on that as soon as that's fully defined. Receivers, that is another body of work that will be undertaken, is receiver development. And then also an update on, well, when can this technology be accessed? And our current plan is to make available the transmitter for NAVTech support in 2025, and also for NAVDAT trials in 2025 as well, so the coming year. So summary, you've seen the NAVDAT modulation. Certainly the complexity is there, but achieving those benefits, as we talked about, requires a very linear transmitter that's capable of wider bandwidth. And then the power requirements flow not just through the transmitter, but also through the ATU and also the antenna. So these are considerations for coastal authorities as they plan for NAVDAT, how to address those additional power implications, what that means for existing facilities, or are there new parallel facilities needed? A positive is that today you can secure through the NAV25, the NAV series of transmitters, a transmitter that can do NAVTEX today and will be able to do NAVDAT as well. And Nautel is ready to help with any of your planning. So we've talked about the extensive digital high power transmission expertise that our companies bring to the navigation space, the new NAVDAT modulator, and the new series of transmitters. We encourage you to follow along and stay up to date. We will be planning future webinars. If you have situations coming up where we'd like to have our knowledge of transmission and modulation involved, we welcome you to request an assessment. And you can see the QR code if you'd like to register for our newsletter and stay up to date and be made aware of events. We encourage you to do that. So going forward, we would love to take your questions. And I'm just going to remind you of the orange button. That is your gateway to get the questions going. And I see at least one question, so bear with me a second here. I can see it here. And Gary has joined us. I apologize. NAVTEX coverage versus NAVDAT. I guess it goes back to that table. Is there the answer is it depends, and I could jump ahead here. It kind of depends on your choice, the trade-offs between power and data capacity. So if you were to choose 1 kilohertz with minimum data capacity, then you're going to get much longer range, maybe comparable to NAVTEX range, but you really will not have fulfilled the promise of NAVDAT. So I'll see if I can flash it up again here, but we did have that slide that talked a little bit more specifically about the range trade-offs. And here it is here. And see if I can, to do this, I have to do an escape. And
yeah, this being said, John, it's not so easy to compare because it's a little bit, we face similar problems with DRM and AM, okay? Because it depends what you call coverage, because for example, in the case of NAVTEX, sometimes, what will happen? The signal will be a little bit, you will have a similar noise signal inside this. The NAVDAT will be like, you will have it or you will not have it, okay? Whereas in NAVTEX, you can have maybe some errors in your text messages on things like this. In NAVDAT, you will get either you will get the perfect signal and the perfect transmission or not, once it's all corrected, okay? It's not so easy.
I have a second question here. It says, why would you use 16 QAM for the TIS when it does not affect the DS bit rate?
This is it would it's a good question. Well, it would affect the DS bit rate, because if you use 60 QAM, you can have more space in the DS as well. This would be my answer. You have to look at the detail at the standard, but this is what it is. I think so. Yeah, because you can win the data that you don't use in the TIS, you can use in the DS.
Great. And I think that is all the questions that have come in so far today. So on that, there's another one. Hang on just a second. So using a 5 kilowatt NAVTEX transmitter, we replace with a 5 kilowatt NAVDAT transmitter will we still get the same coverage? I'll have Herman reply as well too. The answer is maybe. If you move to, if you're stuck with a 5 kilowatt transmitter and you use the narrowest bandwidth and the lowest data coding, then you might have reasonable range, but you've given up the true benefit of moving to NAVDAT, which is the higher data capacity. So it's a, there's not a necessarily straightforward answer. It's more a question of what do you really want to achieve with NAVDAT. There's a question here on antenna requirements between NAVTEX and NAVDAT. 300 feet is our norm for NAVTEX. Gary or Herman, do you venture to answer that, or is that something we would follow up on?
I don't know this one. Maybe Gary, 300 feet.
I think in that case, you know, we would have to analyze the particular site and look at it carefully, because where we're going with higher powers in NAVDAT, of course, you know, the insulators that you have on your antenna currently probably won't handle the peak voltages that will be required for NAVDAT. And, you know, we would have to look at the antenna placement and do a proper coverage study to really be able to answer that question properly.
Yeah, but I think the dimension of the T antenna would be about, you know, the physical dimension. It's about the same, huh? It's more about the antenna robustness and things like this, no?
Yes.
There were a couple of attendees asking, will the slides and the presentation be made available later? And the answer is yes. It may take us 24, 48 hours, but we will post this on our website, and you'll probably even be able to find it on YouTube. So we'll make sure that we make it available. And I think with that, that's the questions that we have today. I guess there are questions that we would ask you to answer as you finish, exit the webinar. You'll find a exit survey that helps us plan for the future and make sure that we're giving you the quality and the type of content that's best for you. Other than that, I'd like to thank you for joining us today, and thanks to Herman and Gary for providing such excellent content and helping us answer your questions. So thank you very much. Until next time, farewell from Nautel and Kenta.
Thank you.
Thank you.